if we know, listen carefully, the number of electrons per unit volume of the conductor of cross-section A and its velocity Vd, average drift velocity Vd, we can determine the current through that conductor as NAE Vd. Next topic for us is the drift velocity. Vd of the electron inside a conductor or semiconductor moving under the influence of the field force. It is the average velocity with which any electron moves due to the force applied I want to know it. It's enough if I calculate the current through any cross section of the conductor to calculate the current through that conductor. At some cross section, check it. Force applied, which will exert the force on the electron. Let E be the electric field intensity. At a point. Maybe same everywhere or different at different points because the conductor is of non-uniform cross section. E be the electric field intensity at a point, magnitude only I am considering. Force experienced by the electron is electron or hole, no, plus or minus C charge, it will have. Magnitude of the force only I am talking about is equal to small e into capital E. You know that. Because E is the field force experienced by unit positive charge. Any charge of E coulombs will experience the force of EE if it is negative charge in the direction opposite to the electric field intensity. If it is positive charge in the direction same as that of the electric field intensity, it experiences the force. Because each electron inside the conductor at that particular point is experiencing the force given by E into capital E, the acceleration with which it moves is EE by small m, where m is the mass of the electron. In fact, it is basically called as effective mass inside the electron because it's a different region with which it moves. You know that F is equal to ma, because of which acceleration is EE by ma. Any doubt till then? Listen carefully now. This is the point of interest for us. And requires now complete understanding of it is really required. If the electron were to be moving in free space, it indeed moves with this acceleration, which says it moves with continuously increasing velocity. It moves with continuously increasing velocity. If it were to be moving through free space. Please understand here. It is not moving through free space. It is moving through crystal lattice. Any cross section of the conductor at 0 degrees Kelvin temperature. Looks like this, in which these are the impregnable atoms for the electron. Electron cannot pass through these atoms. Correct? If at all the electron passes through this cross section, it has to pass through the interstitial spaces only. This is the axis. This is the cross section, right? Conductor is perpendicular to the page now. Only through green spaces it has to go. If it were to be there at 0 degrees Kelvin, there is a situation where if it is a perfect crystal, that's what we use. These holes are seen from end to end. And electron, if it is put into this hole, really travels with increasing velocity and reaches the other end. But when we normally speak about this conductor at some practical temperatures, no room temperature or any extreme temperature or extremely cool or hot temperature, doesn't matter. But we will not be there at 0 degrees Kelvin. Nowhere. If the temperature of this conductor is above 0 degrees Kelvin, these atoms will be vibrating about their mean positions at random fashion. At random. We know that. The bond length of the bond between two atoms, when they define it as at room temperature they define. At room temperature, bond length of the bond between two atoms is defined as what? How the bond length of the bond between two atoms at room temperature is defined? Maybe not. It is the average distance between the centers of those two atoms participating in bonding. Why average distance? Because they will be vibrating about their mean positions. In any practicable temperature, which is above 0 degrees Kelvin, these atoms will be vibrating about their mean positions, because of which they would have come, right? Electron is trying to pass through a particular interstitial gap. Vibrating atom will come and oppose it, stop it. It collides with that and then goes forward, goes backward. And again, because of the force, start traveling. Because there is a force in a specific direction. Net motion will be like that, but during the motion, it collides with many vibrating ions or atoms and moves forward. Isn't it collides now? then again it collides, then again it collides. At so many places it collides actually with atoms and then stops there and then starts moving. Right. Since at any temperature T greater than 0 degrees K, temperature the electron collides many times with the vibrating atoms during its motion. If the temperature is more, you know that an object expands when the temperature is increased because the bond length, average bond length will increase. The distance, average distance between the atoms will increase, because of which it expands. When we increase the temperature, they vibrate with greater amplitude. Because of which the electron will really collide more number of times at higher temperature before reaching the other end. Listen, when it is colliding, and at each collision, if its velocity becomes equal to 0, it accelerates until it collides with some other atom. If tau is the mean collision time, is what average time between two successive collisions. If tau is the average time elapsed between two successive collisions, somewhere it is more than tau, somewhere it is less than tau. Acceleration into time is change in velocity, is velocity. Acceleration into average time, only during this average interval it gets accelerated because it is free. Because of which the average velocity with which it moves is Vd equal to A into tau is equal to capital E small e by m into tau. For a given electron, or for an electron in a given conductor at a given temperature, please see this. At any given temperature in a given medium, given temperature and given medium, tau E by m is constant. And is called as the mobility mu of the electron. Tau E by m is mobility mu. So the drift velocity Vd is equal to actually what? Mu E times the electric field intensity, E to be remembered forever. Mobility is the property of the material. The interstitial spacing, everything will determine tau. And that carefully look at it. Mobility, if we increase the temperature of the conductor, the electron makes more number of collisions per second, because of which mean collision time will decrease. If mean collision time decreases, mobility will decrease, because of which the average drift velocity will decrease, because of which the current through the conductor will decrease. Check it. That's what you talk about temperature coefficient of resistance. If you increase the temperature, electron makes more number of collisions per second. More number of collisions per second means reduced mean collision time tau. So increase in the temperature decreases mean collision time. Reduction in the mean collision time reduces the mobility of the electron, the ease with which it passes through. Reduce in the mobility for a given electric field intensity reduces the drift velocity. Reduction in the drift velocity appears as the reduction in the amplitude of the current. For the same electric field intensity, if you start increasing the temperature, the current to the conductor will start decreasing. I know that. If I consider a simple case where the electric field intensity inside the conductor is created by creating a potential difference of V volts. In the case of the same conductor, if V, I will not show the polarity. Ultimately, I will talk about everything. If V is the potential difference applied between the ends of the conductor, because it is of uniform cross section, electric field intensity E at any point inside is V by L. Voltage applied divided by the length of the conductor will give me the electric field intensity at any point inside the conductor. Now you see, I have applied the voltage between the ends of the conductor that creates the electric field intensity inside the conductor, because of which the electrons start traveling with average drift velocity Vd determined by the other factor by K, basically mu. Because it is the conductor of given area of cross section and the number of electrons per unit volume, the current I through the conductor is what now? What is the current I? I is equal to N E A Vd is equal to N E A mu E times E is equal to N E A mu E times V by L. L into E is equal to V. V by L is equal to E. So the current I is equal to N E A mu E V by L, and we basically talk about resistance. What is V by I? Resistance R is equal to V by I. If I say is equal to what? L by Ne mu E times area of cross section. For a given conductor at given temperature, for a given conductor at a given temperature or given semiconductor at a given temperature, Ne mu E is a constant. and this Ne mu E, which is constant for a given conductor at a given temperature, is called as the conductivity sigma of the conductor. So, if I define the resistance R is equal to V by I, it is given by L by sigma A. You know, L by sigma is the resistance of a resistor of uniform cross section A, cross section area A, length L, made of a material with conductivity sigma. And if you carefully look at it, if we increase the temperature, mobility will decrease, sigma will decrease, because of which resistance will increase for a given length and area of cross section. Sigma is temperature sensitive. We'll meet at 4 o'clock to further this discussion, okay? Resistance. And then we should talk about the resistance. This is actually the resistance that we want to know for transmission lines also. Series resistance along the conductor, right? L by sigma, area of cross section. And I want to later on talk about the field definition of a resistance. We will talk about resistance, right? When we start the discussion at 4 o'clock, okay? Good.